Hey, what's up? Welcome back. I'm glad to see all of you here. So in the past, I think we have all learned mechanical work in either mechanics or in physics. Then have you ever thought about work in thermodynamics? And that is called thermodynamic work. Then let's take a look. So work in thermodynamics is defined as the integral of PDV. This is thermodynamic work. Then before we start, let's briefly take a look at the work in mechanics. So work is defined as force times distance in mechanics. Then if we use Pascal's law, then force equals to pressure times area. Then we plug in the force over here. Then turns out to be its pressure times area times distance. Then area times distance is actually volume. So technically, work can be expressed as pressure times volume. Then this is how work works in thermodynamics, which is the integral of PDV. Then we are looking for a function P with respect to V. So P is pressure, V is volume. Then if we draw a picture, the x-axis is volume, then y-axis is pressure. Then we are looking for a function pressure with respect to volume. So if we know the function P with respect to V, we can plug the function in here, then calculate the work. Then from the picture, also from calculus 1, then the integral of the function is also the area under the curve. So the area under the curve is also thermodynamic work. So it's the integral of PDV. Then the units for work is kilojoule, and pressure is kilopascal. Then volume is meter cube. Then this is the integral form for thermodynamic work. Then if you take a derivative on both the sides, then the left side is dw, then the right side derivative and the integral, they are canceled out. Turns out to be it's T times dv. So this is thermodynamic work, and we are looking for a function P with respect to V, and work is the integral of PDV. The next one, work is not a state property, it's path dependent. So if we are giving a temperature and the pressure, then we cannot determine the work because work is not a state property. We have to know the path, such as right here, it's the volume difference. If we don't have a volume difference, then we don't have thermodynamic work. And similar in mechanics, if you don't have a distance, then you don't have mechanical work. So if we look up the thermodynamic table, then at a given temperature and the pressure, we have specific volume, we have internal energy, enthalpy, and entropy. So all those things, they are state properties. So at a given temperature, and in this case, it's saturated. So for saturated at a given temperature, so the specific volume, internal energy, enthalpy, and entropy, they are a certain number because they are state properties. But you're not going to find anything like work and neither heat because both work and heat, they are not a state property. Then the next one is the sign of the work. The sign of the work will be depending on the pressure and volume difference. So the pressure is always positive. Then we don't have negative pressure. So that doesn't exist. Then the other term is going to be the volume difference. Then if we have the volume difference greater than 0, then we are going to have a positive work. Because pressure is positive, then dV is greater than 0. So work will be positive. Then if we don't have any volume difference, then turns out to be this term is 0, turns out to be no work. So work is 0. Then if the volume change is negative, which means volume decreases, then our work is going to be a negative number. So it's negative work. So as what the picture says, then if the volume increases, then we are going to have a positive work. Then the system does work. On the other hand, if the volume decreases, then we are going to have a negative work. Then the system gets worked. The next thing is specific work. So if we divide it by mass on both sides of the function, then we have specific work. The reason we have a specific work because we want to avoid mass as a variable when we compare different processes, such as if you have a bigger engine and a small engine. So most likely the bigger engine will produce more work than the smaller engine because of the size. So we don't want to have the size to be the variable. So we are going to divide it by the math. So it turns out to be, we are not going to care about the total work, but we want to focus on the specific work. So that's work divided by mass. Then if we do the math, then it's a specific work. The pressure is still pressure. Volume is going to be specific volume. Then we use little w for specific work. Then the units is kilojoule per kilogram, the specific volume, meter cube per kilogram. And it's still dW equals to P times dV. Then let's take a look at an example. An air piston cylinder arrangement, we have the relation between pressure and volume is this expression. And we also know the initial volume and the final volume. So the volume increases. So we expect the thermodynamic work is going to be a positive work because volume increases. And it says compute the work done. Then by definition, work is the integral of PDV. Then plug in the formula and integrate it. Then this is the interval. Then plug them in. Turns out to be this is the work done in this process. So thermodynamic work is the integral of PDV. Did you get it? All right, then this is all we have for today's class. Thanks for watching. We'll see you next time. Bye.